Now, finally, let's go to the conclusion. In the first two videos, we discussed the theory and practice of parts A and B, intervals of increase and decrease, x-coordinates of critical points, and the nature. In the third video, we discussed the theory of concavity and inflection points. Now we are ready to complete this problem. Let's have a little bit of review nonetheless. Here we go. From the graph, we take the zeros of the derivative function. X equals to -3 right here, x equal to 0, and x equal to 3. Those are the critical numbers, or the x-coordinate of the critical points. Not these points. No, not those points either. Here, the graph hits the x-axis. Here, and also here. Those are the critical numbers. Now, these three critical numbers divide the number line into 4 pieces. Less than -3 here, between -3 and 0, between 0 and 3, and finally greater than 3. Right here, less than -3, graph is above the x-axis, so derivative is positive, and consequently the original function is increasing. Here, the derivative is below the x-axis, which means it's negative, so the original function is decreasing. Between 0 and 3, the original function, the derivative function is above the x-axis here, so it's positive. Again, over here, the derivative function, this graph is above the x-axis, positive. That means the original function is increasing and keeps on increasing. And here's the conclusion. Increasing, maximum, decreasing, local minimum, increasing, and that hit this critical point, neither maximum nor minimum, and keeps on increasing. By the way, here is the graph. Increasing, hits local maximum, decreasing, local minimum, increasing this critical point, and keeps on increasing. By the way, one more comment. The maximum, minimum, neither, those refer to critical points. So that should be right above those points. And then those x-coordinate values are -3, 0, and 3 respectively. Now, how about these arrows, increasing and decreasing, or positive or negative? Those refer to intervals, so they should be in between these numbers. If I see these arrows right above the numbers, that's going to be a severe deduction. Not only you screw up the answer, but also you didn't understand the idea of increasing and decreasing. They all refer to intervals. Remember here, positive derivative in the interval, increasing an interval. Okay, alright, now let's go over to the second half of the problem, concavity. So let's copy and paste this thing, and let's go down, and here we go. We have to look at the local extrema of this derivative function. Right here, x equal to -1 and positive 1.5, and finally x equal to 3. Those are local maximum and local minimum of the derivative function. I mean the x coordinates alone. Nobody cares about y coordinates. And what do we have? From -infinity to -1, this graph, the derivative function goes down, decreasing. See, decreasing. And from -1 to 1.5 goes up, increasing. And 1.5 to 3, decreasing. And 3 to infinity, increasing. Do you see that? Decreasing, increasing, decreasing, increasing. Down, up, up. And the change takes place at local extrema. Minimum, maximum, minimum at those points. -1, 1.5, 3. Down, up, up. Consequently, the original function is concave down, concave up, concave down, concave up. Down, up. It's easy. Up is up, down is down. Once you see these graphs increasing, decreasing, going up, going down, concavity follows immediately. At these points, x equal to -1 and x equal to 1.5, x equal to 3, we have an inflection point. That's where the concavity changes. Again, let me emphasize one really important thing. The concavity or increasing decreasing nature, those refer to intervals. So these should not be right on top or below the number. These numbers refer to, inflection point or minimum maximum, those kind of thing refer to the number. So that should be right on top of those dots. Concavity or increasing decreasing, those arrows on the other hand, should be on the interval, not right on top or bottom of the dot. That's, by the way, a common mistake from a lot of students every semester. If you rewrite all those in plain language, here they are. Concave down, concave up, concave down. Concave down. And this should be concave up. Okay, now everything is right. Concave down, concave up, concave down, concave up in all these intervals. In inflection points at x equal to -1, 1.5, and 3. How about the graph? Let's see. From here to about here, concave down, can you see? -infinity to -1, concave down. And then -1 to about 1.5 over here, concave up. From 1.5 to 3, concave down. We have this inflection point, which is also a critical point, and concave up. That concludes a sample problem on derivatives and graphs when the graph of the derivative function is given. There are several other problems here, similar problems with a bit different graphs, and repeat the same thing. And I'm going to leave these problems to each individual students. One more of that. This one looks like has a solution.